Hi everyone. This video starts Unit 6, which is carboxylic acid derivatives. In this first video, I simply want to show you examples of the four main types of carboxylic acid derivatives. They're shown here, going down the ski slope: acid chloride, acid anhydride, ester, and amide. I put them on a ski slope because it's very easy to go down the ski slope, for instance, to make an ester from an acid chloride, but it's quite difficult to go up the ski slope to make an anhydride, for instance, from an amide. We have to take the ski lift, and via the ski lift we'll take the carboxylic acid and convert it to the acid chloride. You'll see what I'm talking about when we start mapping out these carboxylic acid derivatives. At the top of the hill, we are going to have the acid chloride, and then I'll draw the other three derivatives underneath. Alright, at the top of the hill we have acid chloride, or some people call it an acyl chloride. Right underneath we have the acid anhydride, or quite simply just call it the anhydride. Next we have ester, followed by the amide right here. Now there is a fifth carboxylic acid derivative called a nitrile, and that's produced when you take the amide, a primary amide, you form the enol form. Do you remember the enol? And you do a dehydration, you remove OH and H to get the nitrile. So a couple things. Why are these called carboxylic acid derivatives? Because all of these, including the nitrile, can be hydrolyzed to make the carboxylic acid. We will look at hydrolysis a bit later in a different video, but basically what you're visualizing is you are breaking this bond here between the carbonyl on the left and its atom next to it, and you're adding water. Typically you're going to add OH on the carbon of the carbonyl, and the hydrogen would go with what we call the leaving group. Now I put the leaving group in quotes because the leaving group doesn't leave as an anion typically, but visually you can see what I'm doing. I'm just cutting it, and I'm saying that this chloride is the leaving group, Cl-. For the anhydride, we have this. Remember what this is called? This is called a carboxylate, when the carboxylic acid doesn't have its acidic proton. This oxygen anion also has a name. It's called an alkoxide. And the last leaving group from the amide is this NH-. So again, these are called carboxylic acid derivatives. These four. Because when you hydrolyze them, you get the carboxylic acid. Actually, even the nitrile gives the carboxylic acid. In the mechanism, eventually the nitrogen leaves as an ammonium ion. Right now, your main learning objective is to recognize and be able to draw what an acyl chloride, anhydride, ester, amide, and nitrile are. It is important that you are able to recognize these pretty quickly, because when we start looking at reactions, our first reaction is probably going to be how to hydrolyze each of these 5 carboxylic acid derivatives, but mainly we're going to focus on these 4. But then we're going to look at reactions where we could interconvert, where we can go from, for instance, the acid chloride to the anhydride. Remember, it's very easy actually to go downhill. So all of these pink arrows we can do fairly readily in the lab, but also we could go down here, right? That's still downhill, and yes, one of the best ways to make an amide is via the acid chloride. And then what errors are we missing? We could make this anhydride to the amide. So I think we got all of them. 1, 2, 3, 4, 5, and 6. And then yeah, if we have that primary amide, we can make a nitrile via a dehydration reagent that we'll see much later in these set of videos. So again, let's zoom out a little bit. That is basically the outline of the chapter. Now, don't get too excited. There are a lot more reactions than what I've shown here. There's going to be reactions using Grignard. There's going to be different reductions. There's going to be there are actually a couple ways to hydrolyze an ester. And then for most of these, you will probably want to know the mechanism. The last thing I want to leave with before concluding this video is that because these are going from the top of the hill to the bottom of the hill, and I said that it's very easy to make something lower in the hill, what does that imply about the reactivity? That implies that this amide is very stable while this acid chloride is very reactive. Right? Because, see, this acid chloride can make the other 3 carboxylic acid derivatives. So we want to remember that. Again, we will be focusing mainly on these 4 carboxylic acid derivatives, and the acid chloride is the most reactive, the amide is the most stable, and actually that's pretty good, because your proteins, the molecules that make up your enzymes, your antibodies, your transport proteins, those are made via these amide bonds. So you want that bond to be pretty stable. You don't want it to hydrolyze that easily. One last thing. When I talk about the reactivity, I'm just looking at these 4 types of molecules when I order the reactivity. I'm not including carboxylic acid. Carboxylic acid actually is also fairly unreactive, but when we talk about reactivity, let's just limit it to the reactivity of the derivatives. In a later video, I will explain why the acid chloride is the most reactive and the amide is the most stable, or you could even think of it as the least reactive out of the 4. And that's because, I'll give it away a little bit, that's because of, just in part, because of the stability of the leaving group. There are other reasons that I'll go over in the video, but I think the reason that most students like to remember is that that's a very stable leaving group compared to that, right? So the more stable the leaving group, the more reactive, the more likely that molecule is going to undergo a reaction. The less stable the leaving group is, well, that molecule here has no really strong motivation to do any reaction where this is a leaving group, because that is unstable, or that is the least stable leaving group out of these 4.